Welcome, everyone, and thank you for joining us today. My name is Rich Skradsky, and I'm the Northeast Regional Manager for Teledyne ISCO. Before I turn over today's webinar to Darrell Kuta, one of our Flowmeter Business Development Managers, I'd like to take a minute to introduce you to our company. Teledyne ISCO was originally founded in 1958 in Lincoln, Nebraska, where it has remained until this very day. Our environmental division was created in 1969, specializing in the manufacture of rugged instruments used by environmental professionals in the water, stormwater, and wastewater markets. We have been protecting water quality all over the planet for the last 50 years, having invented the world's first automatic wastewater sampler in 1971. Today, Darrell will be presenting on condition-based flow meter maintenance, based on knowledge gained by ISCO over the past 50 years in the industry. After all, we wrote the book on open channel flow measurement, first published in 1978 and updated through 8 editions. If you would like a copy of the handbook, you can request one from our website at teledyneisco.com. We also have an app available called FlowCalc that can be downloaded for free. Darrell will be focusing on the best practices in the optimization of your flow meter maintenance and calibration program, beginning with calibration techniques, followed by maintenance tips, and wrapping up how this can be optimized through the combination of cellular communications, flow meter diagnostic tools, and FlowLink Cipher. We thank you for your business and stand firmly behind our pledge to continue to build great products and provide quality service and support to all of our customers for many years to come. With that said, I'll now hand things off to Darrell. Enjoy the presentation.
Well, thank you, Rich. And thanks for joining me today. As Rich mentioned, I am Darrell Kuta, the Business Development Manager. I've been with ISCO for over 26 years. Many of you may have spoken with me in the past over flow meters, samplers, and the FlowLink software. And today I want to talk to you about condition-based flow meter maintenance. And I want to go over some of the best practices in optimization of your flow meter maintenance and calibration. Some things that I'm going to cover are going to be the principal operation of the common level sensors. I want to discuss a lot about how you can use your sensor diagnostics to be more effective and be proactive instead of reactive with your calibration and maintenance schedules. We'll talk about the recommended locations to take your level measurements on Weirs and Flumes. We'll discuss when calibration or maintenance is needed. And I'll talk about the different techniques for calibrating level sensors, such as using open air techniques or measuring in the water. And then as I go through this, I'll discuss different maintenance items that will help you optimize your flow applications. And finally, I'll finish up with using alarms and cloud-based data to be more efficient. So when should you calibrate? On a schedule? Should you calibrate the first of every month, every quarter? Or should you go out only when there's a problem? Such as this application where you have a debris covering the sensor. Now I'm going to start off by talking about the operating principles of the different types of sensors, because that'll help give us a better understanding of how to use the diagnostics and why we're using them. So I'll cover the submerged probe, ultrasonic sensors, and the bubbler technologies, which are the common level sensors used with Weirs and Flumes. So let's start with the ultrasonic sensor. And some of you have seen this before. An ultrasonic sensor transmits a sound wave, reflects off the surface of the water, and it detects the return echo, which is a function of time between the transmit and the receive signal. Now, all ultrasonic sensors have a deadband, and the reason is because the sensor needs a certain amount of time to be able to transmit that signal and then get the return signal back. And so one thing that's important to remember about that is if you have your sensor too close, it's in the deadband and the sensor doesn't have enough time to respond and receive that return signal. And you may find that when you have high levels and you mounted the sensor too low, you'll find that all of a sudden your sensor goes into error. Other things to remember is ultrasonic sensors use a temperature sensor internally. And the purpose of that is to calculate the speed of sound. And so why that's important is that if you have your sensor in ultrasonic in direct sunlight, the sensor could be and will be hotter than the ambient air temperature, which then calculates the speed of sound correctly. And it actually expects that return signal to come back sooner. And then when it picks up that signal a little bit later, you end up finding that your levels become a little bit lower because it doesn't compensate for that sound or the sound due to temperature. So in that case, you want to make sure you have a sunshade or something over the top of that sensor so it isn't in direct sunlight. Now the bubbler is shown here. It has a built-in air pump, which then pressurizes an air tank, fills it up with air. The air is then released through a control valve, and the pressure transducer reads the amount of pressure it takes to push one air bubble out. And you're going to find that most flow meters output air bubbles at 1 to 2 per second. And then with the ISCO bubbler system, if the bubble line starts to get clogged due to sediment and stuff, they have an automatic purge system that will then send a large burst of air out to automatically clean this. If your bubbler flow meter does not have this feature, what you'd have to do is for regular maintenance is go out there with an air tank, remove the air line, and then blow some air through there to try to clear out any debris that could be plugging that. And what you'll find is that if you have debris covering the end of that bubble line, you're going to see that your level readings are going to start to go higher than the actual water depth, and your flow rate will then also go higher. Now the pressure transducer, it's a differential pressure sensor. And so what that is, it has a diaphragm on the inside that measures the amount of pressure over the top of the sensor. And they have a reference to atmospheric pressure. So through this cable, there's a vent line that goes all the way up to your flow logger or meter that vents to atmospheric pressure. And the reason that's important is that when your barometric pressure changes, if you did not have reference to atmosphere, you would actually see your levels would increase and decrease as the barometric pressure changes. So it's important to make sure that the line is clear, and then you maintain it by replacing the desiccant on a regular basis or as needed. So next I want to talk about the recommended calibration location for weirs and flumes. And so with the weirs and flumes, you're going to use the 3 sensors that I had previously mentioned with the ultrasonic, bubbler, or pressure transducer. Now let's first talk about a weir. So the sensor placement is going to be 3 to 4 times the maximum head height. So what you want to look at when you have your flume is, or weir, determine what your expected maximum flow rate is. You can use the ISCO flow data handbook to then determine, what the level is supposed to be at that maximum flow rate. And then, so in this case, if it was, you expected 1 foot of head height going over the top of that weir, you want to make sure that your level measurement point is 3 to 4 feet in front of the crest or the weir wall. Now the drawdown, as shown here, you want to avoid the drawdown, and that's why you place the sensor back 3 to 4 times from that weir, because you'll have the drawdown effect. If you have it too close, then you can actually be in the drawdown, which would give you a lower level and thus lower flow rates. And as I mentioned, you want to make sure your level measuring point is 3 to 4 times the maximum water head height back from the wall. And your height of the weir should be 2 to 3 times the height of the expected head height going over the top of the weir. And remember, the flow rate is calculated by the water going over the weir, so not the overall depth. So in this case here, if we had 1 foot of water over the top of the weir, and this was 3 feet of water, the weir wall was 3 feet, I'd have a total of 4 feet of water, subtract the 3 feet of like dead space from the weir wall, and your head height would actually be 1 foot. And another important note is that you should have at least 20 times straight run in front of the flume, or the weir, to make sure you have smooth laminar flow coming through there. Now onto the Parshall Flume. The measuring point is going to be in that converging section. And so this wall here is, you want to make sure that you're 2/3 of the way back of this wall length. So if it, just for the easy math on this, if this was 3 feet long, you would want to make sure that your measuring point was 2 feet from the throat of your flume. And once again, in the ISCO Flow Data Handbook, we have some diagrams showing where the location is. But most of the time when you order your flume, you tell them what sensor you're going to put in there, they're already going to put a staff gauge or possibly a stilling well at the proper location. Now the throat on a Parshall flume is going to determine the size of the flume. And then you have the diverging section, which is where you should see your free flow. So when should you calibrate? That could be based on your local requirements. I get this question all the time. So there is no like standard answer, like you should do it every month or every 3 months or quarterly. But sometimes it is, you have local requirements that say you must go out quarterly or at least once a year. So you have to abide by that. Should you maintain every time you go out and maintain the application, like going out there checking for debris and stuff, should you calibrate at that time? It's probably a good idea to verify your calibration and not necessarily adjust it. So depending on your standard operating procedure, if you measure your water depth and you're within 1/4 of an inch, and your requirements may be a little bit different, but if it's within 1/4 inch, or you might not necessarily need to do the calibration, because what I found is that some people, they go out there and they calibrate every single time they go out there, and then they keep adjusting it up and down, and what you end up doing is just keep chasing this calibration. Left it alone, you probably would add more accurate readings. So just check with your local requirements to see how often you need to calibrate that. Now, as far as the ultrasonic, with the ultrasonic sensors, we'll stick with that for a little bit. Now, what we're looking at here on this graph, this is the ultrasonic signal strength, and it's all over the place. Normally with the ISCO equipment, your ultrasonic signal should be at around 90% or higher. When you start seeing something like this, where the signal's going up and down, then you got to start asking yourself, what's causing the problem? Are you having issues with steam or foam or debris that's actually going through there? So it's not necessarily there's an issue with the sensor, but it could be more of the application. Like with this foam, they end up putting sprayers up front to knock down the foam, and took care of the issue. If you had a lot of steam, that could also cause a problem. Now, one thing you could do, if you start seeing ultrasonic signals that are going all over the place like this, is you can test out your sensor by just putting a board or something across your flume. And in this case, it's changing quite rapidly. So after an hour, what I would expect is my signal strength should remain consistent, high in the 90% range. The level would remain consistent. If it keeps moving around like this, even when you're shooting it at a solid target, then you have a problem with that sensor. What could happen is some sensors have ceramic plates in there that are used for to transmit that signal. And if they crack, it ends up creating noise, which could result in something like this. Now, other things with an ultrasonic is, look at your data. And I don't like to look at just a snapshot, just look at a little bit more of the historical data. And what we're seeing here is that every once in a while, we get these large negative spikes. What's happening is it actually is picking up a second echo, as seen here. So this is the diagnostics pulled right out of the ISCO equipment, and this is the return ultrasonic signal. As you can see here, it's got two different peaks. And so what happens is normally it should read this first one to get our level. If for some reason the second one is higher, it would pick that one up. And because this is the distance away from it, it ends up thinking the sensor is further away because the water level dropped. And then you end up with these spikes. Now, the way to overcome that is you should have the ability to adjust your blanking distance. So you want to set your minimum maximum blanking. In this case, if we would have had the blanking at 15 inches and 50 inches, what it would do is it would isolate this area right here and pick up just a good reading, and then it would throw out any additional echoes or bumps after that. And the cause of this could be because it's hitting the top of the flume wall. It could be debris going through there or foam. And so that's what's causing it to pick up some secondary echoes. But hopefully the Flowmeter you have, the programming is smart enough that you can actually set the blanking to correct that problem. Now on to other open air calibration techniques. What we're looking at here is a ISCO 2150 with an area velocity sensor. And to avoid the confined space entry, what you can do is when you're setting up the whole system, get the overall distance, like from the top of the manhole all the way to the bottom of the channel. And so that would be, we'll say this is 10 feet. And so that would be our reference. We'd have 10 feet and then take another measurement from that same point at the top of the manhole to the top of the water. And so if this is 9 feet, take my 10 feet overall distance minus the 9 feet. Now I know that my water depth is 1 foot. And so seen multiple techniques on how people do this. One, you could take a rope or a string, tie a bolt to the bottom of it, and then just lower it down. When it starts to hit the top of the water, you're going to see that the string moves. Measure the length of that string to then give you the overall depth, or just use a tape measure. And once the top of that tape hits the water, you can get your overall distance and then calculate your flow rate or your level. And similar with the in-pipe calibration, exact same thing. So you want to measure from the ID of the pipe, and then you measure the open air from the top of the pipe to the top of the water to then calculate your water height. Now, other calibrations, you can just measure in the water. So what you want to do is just take a ruler and just put it directly in the water and measure from the bottom of the channel to the top of the water. You do want to account for silt that may be in there. And so part of your programming is you want to tell it that there's 1 inch of silt, so you get the proper area calibration. Now, with the ISCO area velocity sensors, they are temperature calibrated. So what that means is that allows you to calibrate your level to 0 in open air, which I find to be a very accurate way to calibrate it. So before you install it, set it to 0, put it in your channel. It'll be temperature calibrated, so you won't see any shifts in the level. When calibrating in the water, you want to make sure you're using like a metal ruler, that thin one. And so you put it in the water and you're trying to avoid having that water rise up on the ruler. And so what I found is that when you have really high velocity applications, you put a ruler in there, it starts to ride up on the side of it. And so it could be anywhere from a 1/4 inch to 1/2 inch off, depending on how much that water is rising up on the ruler. And so that's why you're actually more accurate calibrating in open air, or using the other techniques that I had just mentioned. Because I've been with crews before, and they said they just keep chasing that level calibration because they go out there, the water level's rising up on that ruler, and so they end up creating their own margin of error. Now with the ultrasonic sensors, depending on the flume, a lot of times they will have a staff gauge already built on the side of the flume, which is fantastic. It's a consistent ruler that's in there that's going to help you read your level readings. If you can stop the flow, calibrating 0 level is the absolute most accurate way to do that. However, it's not practical or possible in most applications. So if you have the luxury of having a stilling well, what that does is that actually, as the name implies, it stills the water, so it makes it easy to take your level reading. If you don't have a stilling well, what you can use is a calibration target. And so what this is just a pole with a little platform on it. And so you just set that in your flume. And if you had this height set to 1 foot, you put it in there, calibrate your level to 1 foot, and remove it. So it's a really accurate way to calibrate your level because you have a solid surface. You don't have to worry about the surface of the water. And then it's going to be a very repeatable and accurate way to measure your water depth. Now the Palmer-Bowlus Flume, you can use the same techniques, but I bring this up just because there's always this potential for error. The difference with the Palmer-Bowlus is that it has this riser here. And so this is the 0 point. And so you need to keep in mind, what this offset is. And so if you could stop the flow of water, you'd see that you'd have water pooling up right here, and this would be your 0 level. You set your level to 0, be perfect. But usually you can't do that. So what you'll do is you measure the overall water height, subtract this offset, and then that will be your corrected level. And one of the calls I'd get a lot of times is that, somebody says their flow rates are all of a sudden higher after somebody went out and calibrated. Well, the problem is that they did not account for that offset. So to determine what the offset is, you can determine the size of the flume. So if this was a 6-inch Palmer-Bowlus, I just take the 6-inch divided by 6, and then that gives me a 1-inch offset. So if we measured that overall depth of 4 inches, subtract 1, the level calibration would have been 3. Now keep in mind, because it does have that little offset, you could have sediment in front of that flume, so it may be a maintenance issue that you'd have to go out there quarterly to clean it. Other ways to take level measurements. I've seen guys on the field with just using chalk. And so they'll take their wooden ruler or stick, put chalk on there, put it in the water, and then you just measure, from the bottom of the pole to wherever the chalk line starts to get your level measurement. Others have used washable markers. So if you use like an aluminum rod or something, put that marker on there. The water is going to wash off the marker to make it easy to determine what your water depth is. Now, when is maintenance required? So we're looking at this flume here. You can see it's obviously backed up, so there was a problem. So what are some of the early warning signs? Slower velocity, high level, high flow rates. So those are some of the things that you'd end up looking at. If you had a AV sensor upstream of this application, that would be another way to actually continue to get accurate flow readings. This flume right here, your flow rates are obviously incorrect because it's reading the water depth of a full flume and calculating off that water depth when actually we only have a couple inches of water going through there. But an AV sensor would read the water depth and the slower velocity and continue to give you proper flow rates. So if this was a problem that continued to happen, I would highly recommend putting a secondary sensor upstream. And so you can actually use the velocity to help determine when you have a problem or the level. And so, looking at your data is going to show you that you've got reduced velocity, higher levels, and then you should get somebody out there to do some maintenance. So what are the early warning signs of a potential problem? And so here we got that picture of the AV sensor covered in debris. Now, many AV sensors like our ISCO 2150 and the 350 AV sensor, they store a signal strength. And what that is the amount of reflected energy that's being received from that sensor. The spectrum strength is an indication of the true velocity signal versus the return noise signal. So the first signal strength, how much gain do I need to get a good signal back? The spectrum is tells us how good our reading is. And last, we have a ratio, spectrum ratio, that determines the direction of the flow. So if there's a lot of swirling and stuff, you're going to see a reduction in the signal strength. So what we're looking at here on the left is that we got a strong spectrum and ratio. So what that's showing is that all that water is going one direction, and I got a really strong return signal because there's a lot of particles in that water, and a good return signal back. Now the signal strength over here on the right, what we're looking for is a reading that's going to be between usually in the 40 to 70% range. So we've got a nice uniform flow. We're getting a nice strong signal back. And so what you're going to look at with the diagnostics on an AV sensor is more the trend. What does it start with? And, it's going to be a range of, like I said, usually 40 to 70%. And if there's a problem, like what we saw with that previous picture, as it starts to get covered, the signal spectrum strengths are going to start to drop. So that's where you want to look at the trend and determine when you need to go out and do maintenance. Now with the signal ratio, before I had a really strong signal because everything was going the same direction. If I have something like this with swirling, you're going to see that signal is going to drop. And you're going to get close to 0%. And over here, it's just a lot of turbulence. So that water isn't going any one direction. And so it tells you, what's going on in that flow stream. So if it starts off with a 100% ratio, everything's going one direction, and then all of a sudden it starts dropping down to 20%. Well, I may have some debris or something that's creating, a lot of swirling and turbulence. And so that can be an early warning to send a technician out there to do some maintenance, clean the site before you have an actual problem. And this is just an example of, some of the diagnostics. So what we're showing the velocity, you're getting a lot of dropouts, which could be from debris. And then you're looking at your signal and the spectrum strength. Usually you want it around, above that 40%. If it starts dropping, that's an indication that we may be having problems. So whenever we have the dropout on velocity, we're starting to get a low spectrum strength. And this image is dropping the ratio, but the ratio is starting to drop too, indicating that there was debris in that channel. In this particular case, it had some lower levels that were causing some problems. Now, another way to look at your data is recently had this one where they had the level and flow rate. As you can see, the level and flow was, following the similar pattern. Then all of a sudden, I had it switched. My level went up and velocity dropped. And again, over here on the right, the level went up for a while and velocity went down. There isn't a problem with the sensor here. What it's telling you is that there's a blockage downstream that's actually causing your water depth to go higher and the velocity to drop. So it's just a good indication that, there's a problem. And now I know what I need to do. I need to have the crew actually go down there, clean the blockage out, whatever it is, to fix the problem. In this case, they were fortunate. They weren't able to get out there for a couple of weeks. But so what we can see is my level went higher, velocity went lower, and then all of a sudden they switched again. Whatever was blocking it finally dislodged, cleared out, and so they actually didn't even have to go down there and clean it because the problem essentially resolved itself. It doesn't always happen, but they got lucky in this case. And you'll notice the flow rates, even though these switched, the flow rates remain fairly consistent because we got the same amount of water going through there. It's just that the dynamics have changed, with higher levels and lower velocity. Other things to look for when you're looking at your data. So say you have a sensor that doesn't have the diagnostics with the signal and spectrum, but you just have velocity. What you want to look for is anytime you have flat lines in your data, that indicates there's a problem, because there is no way that velocity is going to remain that consistent for a couple hours. Other things you may see is in the scatter plot where you start getting this rowing. And so when you get rows like that, that's a great indication that, it's just locking onto a reading. So you're not getting any new readings. So whatever this water depth was, it just held onto that velocity for, hours at a time. So it just indicates that it wasn't updating. And then you need to investigate what the problem is. These readings here with these flat lines, I believe it was because the water depth was too low. It wasn't able to pick up the velocity reading. And, so then it just flatlined. But they're just things to keep in mind when you're looking at your data. Other diagnostic tools, if you have any type of signal strengths, like as mentioned before, look at the trends. If you see that this is a bit exaggerated in this example, but if you see that it's starting to drop, in this case where it was starting out at about 97%, and then all of a sudden it starts dropping down here to 55%, you may have to set a reminder or an alarm that anytime your signal strengths drop below 55%, you should send somebody out there to investigate or clean. And they clean the sensor, clean the debris off of it. Now all of a sudden the readings go back up. And so this is the same. This applies to any type of signal strength. Just look at what it starts with, and and you're going to see historically that it's always going to be in a certain range. But then if it starts to drop, that's going to be your alarm or trigger to tell you to go out and do some maintenance on that site. Now this graph here, what we're looking at is level, and you can see it's actually going below zero several times. This is an example of where your sensor no longer has reference to atmospheric pressure. And so as the barometric pressure changes, all of a sudden now all my levels are going higher and lower. And that's usually seen by, levels that are going to go one direction, or it actually goes above and below zero instead of remaining consistent. So the first thing I would do when I see data like that going below zero is replace the deskant, because the sensors have a reference to atmosphere. And if your deskant is old or damp and it's no longer able to essentially breathe, you're going to cause that type of drifting. So it's usually quick, easy maintenance to replace your deskant. Other cleaning techniques, I see a lot of field crew. Essentially, they go out with the broom, or they fabricate a pole and put a broom head on there and just simply brush off the top of the sensor to clean that debris out of there. If you do remove the sensor, usually just use tap water, and try not to touch the sensor directly, because usually it's just like a thin aluminum shield that's filled with oil, and you don't want to damage the actual transducer, but but just run some tap water over the top of it, usually to clean the sensor. Now, if you do have problems with debris where you have to go out there quite often to clean that application, one thing you can do is just offset the sensor, move it, rotate it up to the side. That way all your debris and everything just falls to the bottom and washes right past the sensor. Now, keep in mind, normally you're calibrating your sensor to zero right here at the bottom, but if you rotate it, and then you would calibrate it to the actual water depth. So if this is 6 inches, I calibrate the level to 6 inches here at the bottom. If I rotate it to the side, I still calibrate my level to 6 inches, and it should continue to track properly with the change in level. Other options, if you have silting, switch to a non-contact sensor, such as the LaserFlow sensor, because this will use the ultrasonic sensor to read the distance to the water. It calculates the level for your flow calculation, transmits a laser below the surface of the water. And the difference here is actually reading the peak velocity. It takes 5,000 spectral readings in 2 seconds to get your peak velocity to then calculate your average velocity for your flow rate. And it will also determine the frequency shift and the speed of the water. Now here's what the diagnostics look like on a LaserFlow sensor. So when that laser is on for 2 seconds, it develops this curve, and this is the area under the curve. So when it takes those 5,000 readings, the more the readings agree with each other, the tighter this bell curve and the higher it's going to be. And so if it was if we had a lot of turbulence and swirling water, like the poor ratio, you would end up seeing this signal being much lower and wider, indicating that there's swirling, possibly from debris in that channel. So again, you want to look at the historical data. You know, when everything's first installed, I get this good signal, and all of a sudden it degrades. It gives me an idea, you know, where the noise is coming from, and then I can send crews out to resolve the problem. Other diagnostics that are available to you, especially on the LaserFlow we're seeing here, we got ultrasonic signal strength. We already talked about that. We can it'll tell us the distance to the surface of the water, which is easy to measure. We can read the X and Y axis, so that's going to tell us if the sensor is still level in that application. And when you want to look at that, say maybe after the sensor is submerged, instead of just sending somebody out there immediately, you can look at these. You know, if I still got a strong return signal, my X and Y axis shows that it's still level, I don't necessarily need to send somebody out there to the site to take a look at it. I can look at the air temperature to let me know my ultrasonic sensor's reading properly. And then we've got Doppler power, which is that return signal. So with the LaserFlow, you have a lot of built-in diagnostics that you can look at and determine if you need to go out there and do any maintenance. So this can save you a lot of money in the long run. Instead of just arbitrarily sending a technician out there, use the diagnostics to let you know that everything is still working properly. Some additional diagnostics that are actually built into the system. So it tells me that the step count, how far the laser's actually transmitting away from the water, the focus depth, how far it's going below the water. I can see my X and Y angle, that it's still level in there. It should be X should be 0 plus or minus 3, Y is 45 plus or minus 3 degrees. So I know everything is still good at this application. Now, out of all these diagnostics and levels and readings, you can use this for automatic alarming. So you can trigger off of level flow rate. You know, if your level is greater than X, your flow rate's less than 10 gallons per minute because it's surcharging, your signal strength is dropping. You can use all these to determine when to send crews out. And so how you can do that is use a modem. Modem, Ethernet, IP address, send that data out to the cloud or have it call you. If you have a modem on your equipment, it can automatically send you a text message, or you can use your SCADA system to send out your alarms via Modbus or analog. However you have to do it, use the tools that are available to you for your diagnostics to determine when you should go out to those sites. Other things on the LaserFlow sensor, we do have what's called sense voltage. And so what that is that if the sensor, the window starts to get condensation on there, it will automatically turn on a heater to tell us when. The heater will turn on to clean the window off, to minimize maintenance. What we're looking at here is just an example of what we'd shown before. Just look at the overall trend. If it starts to drop, that's when you should go out and clean your sensor. And this is an example of the optical clarity system. If it starts getting condensation on there, it will automatically turn on the heater to clean that window off so that you don't have to go out on the site. And as I mentioned before, we want to look at the trends, not the instantaneous reading. So we started getting condensation on the window, heater kicks on, drops it back down, condensation goes up again, heater kicks on. So we don't lose any data. It's just automatically warming up that window, cleaning it as needed. Other things you can do to test a LaserFlow system, if you don't have water running, what we've done here is they put a record player down there. The laser can read the speed of the record spinning, and so the velocity actually changes as you get closer to the center, and it gets faster as you get to the outside. Or what I like to carry with me is just a little USB fan. So it's just a quick and easy way just to test the mechanics of your system to verify that it actually is reading the level and velocity. Now, finally, on the cloud-based software, benefits of cloud-based software is that one, it minimizes the maintenance. You don't have to have a server involved. So the data is automatically can be pushed out to the cloud where you can view it on a dashboard or on a map to see your sites. Gives you the option for quick analysis. So everything I'm looking at, you can easily look at that dashboard, see what's going on with your location. You can even program alarms where it would quickly notify you when you have a condition where you may need to go out and do maintenance. And the best of all, it's the data anytime, anywhere. So you can look at it on your cell phone, laptop, wherever you're at. 3 o'clock in the morning, there's big rain events going on. You can easily take a look at your data to see what's going on at your site. And the biggest thing with cloud-based software is that you don't have to have a server. So this is all done remotely. You don't have to worry about the IT department maintaining it, updating firmware. It's all going to be done in the background. Now, the dashboard I mentioned, this is just an example of your intuitive dashboard. So you can have a graph showing level, velocity, flow, signal strengths, scatter plot, as it's shown earlier. If you start seeing that rowing, then you got a problem. So, if you have a scatter plot that always updates, you just want to make sure you got a good, nice, tight pattern. Alarming. Like with the Flowlink Cipher software, this apple tree has a red hue around it, indicating that it had an alarm condition. So I can easily identify, I have one site that may be having a problem because of the low signal. Now I know I need to send crews out. And as for alarm notification, many flow meters, the ISCO flow meters can send a text message directly from the meter to let you know that a condition has happened, or you can get the alarm from your server, from the Flowlink Cipher. It can send you a text message. It can send you an email, and you can direct it to whoever needs to take care of that. Maybe it's low battery, and so they need to send crews out for maintenance. And so you can send maintenance alarms based off of low signal over a duration of time. So again, we don't want to look at instantaneous readings. So if we see that I've got signal strength at 30% for 1 hour or more, then that would be my trigger to send somebody out. Other things you may want to look for in a cloud-based software is, make sure you have the GIS mapping. This pin here would actually change colors to let you know that it's in an alarm condition. You may want to look for software that allows you to put attachments on there, so that way the crew they can easily look at it just as a reminder what they need to take out to that site if they have to go out for maintenance. So I covered a lot of stuff on different sensors, locations, software. If you have further questions, please use the Q&A function or contact me directly or your local ISCO representative. If you don't know who your local rep is, go out to our website, isco.com, and there's a link for Find Your Rep or distributor, and that'll get you directly to your local person, or you can contact me at darrell.kuta@teledyne.com. I noticed in the chat function today, we had a lot of good conversations going on. I appreciate that feedback you had over there. Do want to address a couple things. One of the questions was, as far as the annual calibrations, it must be within 10% of the true value. And so, yeah, if you're required by local regulations to go out there once a year or quarterly, you have to follow those regulations, and then they also set usually the guideline on that. If it's within 10%, or as Dan mentioned, it maybe needs to even be tighter than that. And One thing I caution against going out there and calibrating every time, when it's only off by a little bit is, sometimes you find they end up just chasing a calibration. So one time somebody goes out there, they adjust a little bit higher. The next time they adjust it about the same amount lower. So you kind of keep chasing that calibration back and forth. So you just want to be careful of that. And that's especially true when you have, locations at the steep slope where you got low level, high velocity. It makes it really difficult to calibrate. And so that's where you want to, use the open air techniques, or, try to calibrate in the open air. Another thing that was mentioned on the chats was the using the color cut. Appreciate everyone's feedback on that. I was not aware of that product. I've heard of it, but I didn't know the name of it. And so those of you that didn't see that in the chat, that color cut is a paste that you would put on a pole or a rod or something and put in the water, and it changes colors to make it easy to determine what your water level is. So I thank you guys for your feedback on that. Let's see. Somebody was asking about if we could touch on the atmospheric calibration on the 2150 sensors. So just a little background on that again, we temperature calibrate these sensors. And from 0 to 10 feet. So what that allows us to do is that when it is in open air, you can set the level to 0 and you put it in the water, and you should get an accurate level reading because it automatically adjust to the temperature. Some sensors that do not have built-in temperature sensor will, you have to actually put it in the flow stream, let it acclimate, and then calibrate your level. And let's see, part of that same comment, sometimes they get negative numbers when they do it. I guess that I'd almost need a little more information on as to how deep the water is. If you're putting it in a 1/4 inch of water, or if it's a little bit deeper. Yeah, I guess I'd have to get a little more information on that. But what else? We had another question before about the deadband on the LaserFlow sensor. So that does have a 10-foot range on it, and the water level can come all the way up to the bottom of the laser. So it's essentially a 0 deadband. So it'll continue to operate all the way up until the point it starts to become submerged. And if you do have an application that has potential for submergence, we can take an area velocity sensor, mount it on the bottom, so then it would switch technologies to the pressure transducer and the continuous wave Doppler to continue getting flow readings. And let's see. And yes, Dennis McGinnis is sponsored by Nike. There's another question that came in about the minimum flow necessary to receive a signal on a 2150 AV sensor. So as far as it needs about 1 inch of water to completely cover the sensor to be able to read velocity. To read velocity, it'll read level down to about 1/8 of an inch, but it does need to be completely covered to read velocity. The low range on it, I prefer to see velocity at 1/2 foot per second or higher, but usually the 2150 can easily go down to about 0.3 foot per second. Anything below that, you could start having problems with the reading velocity. And the particular question they had sounded like they had a Weir system somewhere behind the sensor that was actually damming up the water, probably trying to create a higher depth to read velocity, but there comes a point where that water isn't moving fast enough for it to read it. We had another question on signal ratio. I see the signal strength, and the signal spectrum, but where's the ratio reported? So on the 2150 sensors, while you're connected to it, there is a jump to measurement option towards the top right. You hit that drop down, and that will give you the option to enable or turn on the spectrum, signal, and the ratio. And so I do like using the ratio. It's a great way to determine the direction of the flow, especially if there's any type of debris in front. You end up seeing that ratio drop. Another question that came in is, what's the best method for artificially raising the depth in a shallow flow without creating a hydraulic jump? Yeah, that one's tough. Because yeah, it depends on your location. I've seen people just take some small sandbags and just actually drop it in the stream to artificially create a higher head height. And I've seen others that have taken like a spring ring, and then they put a small, like a round, try to put a plate in the bottom of it to raise that head height. And so the spring rings are usually for 15-inch pipes and smaller. And there is some problem, potential for issues when you do have to dam up that flow stream, because then that is a place to start catching debris and sediment. So you may have to do a little more maintenance there. That actually could be a great application to consider using the LaserFlow sensor, because it can read the shallow depths and the slow velocities without having to try to create an artificial head height. And let's see if we got anything else. Well, that seems to be about it for the questions for right now. My email address is on the screen there, darrell.kuta@teledyne.com. And so if you have additional questions, feel free to reach out to me, call me, email me, contact your local rep, or email Sharon, the host of this presentation, and we'd be happy to get the answers for you.
Well, thank you, Darrell, for sharing your expertise, and a special thank you to all who have attended the webinar today. As mentioned earlier, it was recorded and a video will be made available in the near future. If you would like a certificate for your attendance, please email me indicating the title of the webinar and how you would like your name to be indicated on the certificate. We then will fulfill your request. I would also like to share you will be receiving an email from me which contains a survey link. Please complete the survey for us, because this helps us determine our following webinar topics. Thank you again for joining us, and have a great rest of your day.